In this demonstration, we're going to see how we can model a DC motor using the physical modeling method. The system we wish to model looks like this. We have a DC motor with electrical inputs that is connected to a rack and pinion to produce translational motion. We wish to model this using the physical modeling approach. We'll do this using Simscape. The model we build will look like this, where we can see electrical and mechanical components connected using physical connections. And we'll see when we run the simulation the results from the mechanical and electrical portions of our system. I'll now switch over to the model so you can see how this is done. Simscape can be found in the Simulink library browser. We'll build our DC motor model in this empty Simulink window. First, we'll need a DC voltage source. We'll get that from the Electrical Sources library. Next, we'll need some of the electrical elements in our circuit. We'll take a resistor, an inductor, and an electrical reference and connect them to each other using physical connections. These physical connections represent ideal electrical connections between the electrical components. We'll want to measure the current from our circuit during the simulation. We'll do that using a current sensor. We'll view the results of our simulation on a Simulink scope, which comes from the Sinks library. The output of the current sensor is a physical signal. The physical signal has units associated with it. We'll use a converter block in order to assign the units of amperes to the signal that we're going to view. We'll connect this to the sensor block and then to the scope. Simscape uses solver technology above and beyond what is available in normal Simulink. To have access to important settings, we'll use the solver configuration block. Finally, we'll need to use a Simulink solver that's recommended for physical systems. We'll use ODE15S. At this point, we can run the simulation and see the current produced. We can see that the current remains at 1 amp. Next, we'll model the mechanical portion of our system. To convert electrical power to mechanical power, we'll need a rotational electromechanical converter. This block allows us to exchange power between the electrical and mechanical portions of our system. It has 2 electrical ports and 2 mechanical ports. This mechanical port represents the shaft of our motor. We'll go into the mechanical rotational elements and get an inertia block. We'll rotate that here and connect it here. This port represents the housing of our motor. We'll want to make sure that the housing doesn't move, so we'll get a mechanical rotational reference block and connect it here. Now we can rerun the simulation and see what effect these components have had. You can see that the current slowly drops as the motor comes up to speed. We'll want to add some damping to our motor, so we'll get a rotational damper block and connect it here. Now we can rerun the simulation and see what effect this has had. You can see that the motor now reaches a different final speed. We'd like to measure the speed of the motor. We'll go to Mechanical Sensors Library, get a rotational motion sensor, and connect it here. We'll connect one end to the shaft and measure the speed of the shaft with respect to the housing. We can copy these blocks in order to view the results on a Simulink scope. We'll connect it to the speed port and assign the units to be revolutions per minute. Now when we look at this scope and run the simulation, we can see that the speed of the motor reaches a final speed after about 6 seconds. Our motor needs to produce translational motion. To do this, we'll go to the Mechanisms library and get a wheel and axle block. This will take the rotational motion of the motor shaft and convert it to a translational motion. The load that we're going to apply to our motor is a spring. So we'll take a translational spring and connect it here. This spring needs to be attached to ground, so we'll go to Translational Elements, get a mechanical translational reference, and connect it to the other end of the spring. Now the motor will have to stop when the load reaches the value that stops the spring. So we'll rerun the simulation, and we can see that the speed of the motor oscillates as the motor attempts to act against the spring. If we take this signal and attach it to the A port, we can see the angle that the motor reaches. We'll display this in degrees. I'll rerun the simulation, and we can see the effect that it has had. Again, the motor acts against the spring and we see oscillations. If I weaken the spring, we can see that it will fairly quickly reach its final value, which is somewhat less than a rotation, less than 360 degrees. If I want to see the source code behind these components, I can simply double-click on the block and click on View Source. Here I will see the Simscape language code that was used to implement these blocks. Here you can see that it looks very much like MATLAB code. In this demonstration, you have seen how we can model a DC motor using Simscape.